So hi everyone, welcome back to my YouTube channel. This is Mansa. I'm currently pursuing my first year BA in Sri Venkateswara College of Engineering, Bangalore. So today in this video, let's discuss how superconductivity is used in quantum computing. So first, let's get into the introduction of this topic. So superconducting quantum computing is a branch of solid-state quantum computing that implements superconducting electronic circuits using superconducting qubits as artificial atoms or quantum dots. So many recently developed quantum processing units or quantum chips use this superconducting architecture. So research in superconducting quantum computing is conducted by many famous companies such as Google, IBM, IMEC, etc. So the superconducting quantum computing devices are typically designed in the radio frequency spectrum, cooled in dilution refrigerators, and addressed with conventional electronic instruments, for example, frequency synthesizers and spectrum analyzers. Manufacturing superconducting qubits follows a process involving lithography, deposition of metal, and collection of oxidation. So now let's see the working of superconductivity in quantum computing. So one distinguishable attribute of superconducting quantum circuits is the use of Joseph junctions. So Joseph junctions are an electrical element which does not exist in normal conductors. A single Joseph junction where C is a thin layer of insulator. On the top of the slide, you are able to see a diagram, a picture, where C is a thin layer of insulator, A and B, so that is superconducting currents with non-equivalent wave functions. So the resulting Joseph junction device exhibits the Josephson effect, whereby the junction produces a supercurrent. So the current flow through the junction occurs by quantum tunneling, seeming to instantaneously tunnel from one side of the junction to the other. So to understand how superconducting qubits work, we need to get into a question. So what is that? Why do conductors allow for the easy passage of electrons in insulating materials does not? So solid state physics tell us that when an electric current travels through a material, the electrons therein come into two types. Conduction electrons flow freely through the material, while valence electrons are attached to the atoms that form the material itself. A material is a good conductor of electricity if the valence electrons require no energy to be stripped from the atoms to become conduction electrons. Similarly, the material is a semiconductor if the energy needed is small, and it's an insulator. However, superconductors do have infinite conductivity. It's not a phenomenon that we see in our daily lives. For some materials at extremely low temperatures, the conditioned electrons attract the positive nuclei to form regions of high positive charge density, alternating with regions of low charge density. So this charge distribution oscillates in an organized manner, creating waves in the material known as phonons. So the conduction electrons are pushed together by these phonons, forming a Cooper pairs. So most importantly, these coupled electron need not obey the exclusion principle. We no longer have an electron population limit in the low conduction energy levels, allowing for infinite conductivity. So let's know the challenges in superconducting quantum computing. So superconducting quantum computing must also migrate quantum noise as well as leakage. The leakage in the sense information being lost to the surrounding environment, and also the future superconducting quantum computing. The sector's leading industry gains like Google, IBM are using the superconducting quantum computing to make leaps and bounds in the area of quantum computing.